Hi, everybody. My name is Ricky. Thanks, Holger, for the introduction. Really appreciate it. And to the Viverica guys for inviting me to the conference. Really appreciate it. So today I'm going to be talking about real-time metrics at Fortnite Scale and what that means for us at Epic Games. So quick overview on the agenda. We're going to be talking about getting insights using metrics, which is something everyone's very familiar with. We're also going to be talking about conquering unstructured data, or really data doesn't necessarily have a schema, and you're not imposing a schema on a developer. We're also going to talk about how we built self-service at the forefront of the product, and also we're going to talk about reducing the barrier of entry, which is a really important aspect of when you're building a product, whether it's internal or external. You want to make sure the barrier of entry is as low as possible. So a little bit about our team. The team I work on and the team back here in Raleigh and all over the place, we're the real-time streaming data platform team. We're currently around 8 engineers. And if anyone in the audience finds any of this stuff interesting, we are hiring and we would love to get an application from you. So a little bit about Fortnite for people who aren't familiar. It's a free-to-play battle royale. It's available on most platforms, hundreds of millions of players, and we're getting terabytes of data an hour. So to kind of talk about what we're facing, we're getting millions of event payloads a second. We extract this data out as it's coming in, and that's kind of what this talk is about. And most importantly, the event schemas are not concrete. There's no set schema that a developer has to follow when they're sending data to us. So talking about event payloads, what would an event payload kind of look like in a video game like Fortnite? Well, the payloads are sent from like game clients and servers. So a game client, like a PlayStation or Xbox or Switch or something like that. And then the servers which are hosting the games. And the events contain a lot of pertinent information, like performance data, user interactions, lobby information, and a whole lot more. And we continue to add more information upon every release. So like a very simple example of like what you might find in a event payload. It's like maybe like you got the account ID, what platform the user's running on, what country they're in, or maybe region as well, and maybe their ISP as well, along with a ton of other information. This is a very, very small example. So what are we trying to solve? We're trying to solve metrics through JSON extraction, meaning we have some arbitrary JSON being sent to us, and we want to extract some sort of meaningful metric out that we can take action on. We never want to impose a schema on the developers, which is really one of the hardest parts, but the most important part. We have this schema on read mentality, where we're not telling the developer that, no, you must fit to this schema in order to use our product. You just send us whatever, and we can figure that out after. And the workload is completely user-driven. So without the users, our Flink clusters would just be sitting there doing nothing. They would be receiving data, but they wouldn't be extracting any data. So this is kind of what we're trying to solve. Along with the previous bullet point, we're also trying to have zero downtime user-injected workloads. So if a user decides at 3 o'clock in the morning that they want to start extracting a specific field out of the JSON and start doing some sort of aggregation on it, they should be able to do so without ever having to bother us. They don't have to go through a release cycle or anything like that. It's online in minutes. So let's talk about conquering a use case. Let's talk about a very simple use case like concurrent users online. So what is that? That's we're trying to count how many unique players are online at a given time. We may want to break it down by platform as well, like PS4 versus Xbox versus mobile, and so on and so forth. And maybe you want to break it down even further, which is kind of what we're going to be talking about, both platform and region. We also want people to be able to define custom time windows. So hourlies, dailies, weeklies, maybe every 5 seconds, every 1 minute, things like that. It's completely up to the user. So let's strategize on like how we would even go about doing this, right? So we're trying to extract arbitrary fields from JSON. So maybe like matchmaking time or the account ID, for example. We also want to group on arbitrary fields. So like the platform, the region, the ISP. And we want to be able to perform some sort of aggregation over the numerical or non-numerical data, depending on the aggregation type. So like count, sums, min, maxes, percentiles. We're going to be talking about the last one here, hyperlog, which is a way to perform an approximate count distinct on a certain field. And we also want to be able to round timestamps based on the user needs. So I'm gonna try to visualize that here in a minute and make a lot more sense. So we have a payload, kind of what we saw earlier, except now I have a timestamp field. We want to extract some data out of that. So we're gonna I want the value, and I want the grouping key to be a compound key of the country and the platform. And the timestamp is kind of interesting, right? Because this timestamp comes in at whatever interval. Just so happens the game's fired off at this second versus another second. So in this case, it's hour 16, minute 39, second 17. But we want to actually group on every hour. So how do we do that? We're going to just shift that timestamp forward. So 1639, we're just going to shift it forward to the 1700 hour. And of course, this is going to be user-driven, as user-defined, rather. So let's talk about the original version that we had running. It was built on Kinesis, Apache Spark, DynamoDB, and we actually ran it in production for 2 years. But we had a lot of shortcomings that we ended up figuring out along the way, and kind of led us on our journey over to Apache Flink. So scaling beyond sub-minute aggregations was virtually impossible. And that was probably the hardest thing to solve, especially with Spark. There's a lot of overhead with the RDDs and such. We had data corruption with multiple producers was an issue that we had to solve. We had to do some very clever mechanics talking to DynamoDB because we have multiple clusters writing to the same destination. And that was probably another really difficult thing to solve. Another thing was like if a cluster went down and we had to catch back up, large bursts meant rate limiting, which was another difficult thing. Failover took minutes. We had a lack of binary persistence in DynamoDB. And we had no real control over how DynamoDB was performing its balancing strategy in the storage layer. So we have to say goodbye to that old product, but definitely a good friend at the time. But this really kind of brings up the next problem. How do we like evolve from the previous implementation? So what are we looking for? We're looking for high throughput ingest pipeline, a high throughput ingest pipeline. We're looking to do online sub-second aggregation. So we don't want to wait minutes for an aggregation to populate. We want it online in seconds. And we want viewable metrics in seconds as well. And this is a difficult thing as well because we're going to aggregate it and we need it to be in front of a user within seconds. And another thing that we ended up finding out we needed was the ability to do some sort of transactional update of partial metrics. And I'm going to talk about the 3 pillars that we kind of came up with. And I'm just going to double check real quick that everyone can see me and I'm not. Okay, there we go. Okay, so the 3 pillars. The first pillar we started to investigate with was Apache Kafka. To move over from Kinesis to Kafka. We also were really impressed with a lot of the work that Apache Flink was doing, so we wanted to go ahead and test that out. And finally, we were really impressed as well with a database called FoundationDB, which is I'll show you that here in a second. So Kafka, I'm pretty sure everyone here is very familiar with Kafka. We're using it as a monolithic event fire host. So basically a single topic where all the events from all the game clients and the servers are just pumping JSON through. And these are all packed in and sent off. Mainly, another thing is this supports gigabyte second throughput, which is extremely important when you're scaling a game like this. And it also supports group-based consumption, which I'm not going to talk about a lot in this, but we use the group-based consumption model wrappers in Apache Flink, so we don't do static partition assignment. So Apache Flink, I'm sure I'm preaching to the choir here, but it's very well maintained. It's not micro batching based, which is something that we were really liking when we were investigating new technologies to use. It has a highly efficient internet communication. The serialization, deserialization stuff, we basically never really had to worry about it. And yeah, we found out it performs aggregations very fast. And met our needs, actually. And another thing, similar to Spark even then, which is I can unleash the power of the JVM. So we have Scala, we got JWay, gRPC, and different things like that we can actually utilize within it. And the most important thing, I suppose, is the workload can be dynamic because we're programming this pipeline. We're not using SQL or anything like that. This is all programmatic pipelines that we're going to modify and augment during the life cycle of the system while it's running. And last pillar is FoundationDB. It's a highly scalable and durable key value store. If people are familiar with HBase, it's very similar in that you have a binary or a byte array key, a byte array value. There's no columnar comparison, but it is a key value store in byte array to byte array. And the data is naturally fit for time series because everything is stored in lexicographical sorting, which makes it really efficient for that stuff. But again, binary focused storage. This ends up being really important because we want to be able to store hyperlog logs, for example, and store it as bytes. But another thing, it has very strong transaction guarantees, which is really awesome to see for a key value store. You don't really see that a lot. And that comes in handy when we have two people trying to write to the same row, and one wins and the other one fails the transaction and has to retry. So you don't have any kind of data inconsistencies or really like data corruption. We have the utmost confidence and stability. It's very well tested, very well maintained. That could be an entire other talk, to be perfectly honest. So the kind of like flow of the data kind of looks like this. We have Kafka, data coming into Kafka, it's going into Flink, data goes back out to Kafka, and then we have another thing that writes the data to FoundationDB. And this is all happening, millisecond speeds. And then the user queries FoundationDB, which we're going to talk about. We actually have a front end, which technically is not really the user. Diving a little bit further into the actual Flink application, what does that look like? Well, payloads are coming in. So event payloads that we talked about earlier, we're extracting metrics out of these payloads. And the metrics that we're extracting is a user-driven, parameter. So users might have hundreds, maybe thousands of these extraction definitions, and they want to retrieve out some numerical values out of these metrics, and then they want to perform an aggregation. Once the aggregation is performed, then we write it out. An aggregation we're doing every 2 seconds. So data's coming in, metrics are firing out, it's buffering the data in the aggregation engine, and then it fires out the final aggregation result, which can be grouped on different arbitrary fields. So we have the three pillars that we discussed. We're going to take our high throughput ingest. I'm going to drop that right here in the cauldron. Then we're going to take our sub-second aggregation engine, which is, to put it lightly, Apache Flink. And we're also going to take our transactional update system, so our key value store, FoundationDB. And out comes this product that we call Metrics Royale internally. And to kind of go back to Apache Flink, since this is after all, Apache Flink conference, I'd like to talk about like the power that we kind of saw in Apache Flink. And I think a lot of its power also comes from just the JVM. JVM, you're going to be able to use Java libraries. There's tons of Java libraries out there. So you're not having to reinvent the wheel. And sometimes a library might inspire you to do something, which is kind of what happened with JWay. We're going to talk about JWay here in a minute, but just know we heavily utilize it in this product. We found Scala was actually really great for data-driven workloads. It's actually really nice. And Flink's custom aggregation capabilities made it even easier for us to build this kind of dynamic workload system. So to kind of talk about JWay, JWay and users together is very powerful. JWay is essentially JsonPath and a JsonPath implementation in Java. It's kind of like XPath, if people are familiar with that. It's kind of like XPath for JSON. It also supports like filters for conditional use. I'm not going to really dive too much into that, but just know it allows a user, when they create a metric, they can say, well, I want to extract metrics out of this JSON, but only JSON that kind of looks like this and meets these parameters and conditions. And it allows us to do runtime injection because it doesn't have to be compiled ahead of time. It's like regular expressions. You can, in theory, a user can define a regular expression in a server if the server allows for the input. So kind of go back to the payload again. Let's talk about like the power of JsonPath and how JsonPath allows us to perform that extraction. So if we had like a grouping key as like an array of like the country and the platform, then we would be able to extract out a couple of fields for the grouping key, and as well like for the value. So the value in this case is a non-numerical value, but we're going to perform a hyperlog over it, which does its own thing. And we also define the timestamp. So in this given scenario, the user's like, okay, the grouping key is these values. The value that I want to pull out is this field. And this timestamp field is what we want to use for the timestamp for rounding. So what's extracted? Similar to what it looked like earlier, we're going to be able to get that grouping key out. We're going to put together both the country and the platform together as a compound key. And then we're going to be able to also pull out the time or the account ID for the value, and then the timestamp as well. But again, we kind of run in this issue where it's like, okay, with the user aggregation, the timestamp happened to be 1639. The user is going to define, well, our aggregation type is a hyperlog log. We want to perform it every hour. So we want to basically roll up this aggregation for every hour. And these aggregations are happening every 2 seconds. They're just rolling up. And we want to perform this rounding strategy of forward. What this really means is we take this timestamp, which is 1639, and we forward round it up to the next hour. If we use the rounding strategy as backwards, then it will go back down to the 16 hour. We always use forward hour rounding. It just makes more sense for a lot of this stuff. So to kind of demonstrate very, very simply of like how the hyperlog log works, we have this key, which is the hyperlog log, and the key is the region and the PS4. That's like kind of in Flink, key by. That's essentially what this is. And as well as a timestamp. So we got this user, his name is ABCDEFG, and that's going to go into the hyperlog log. Well, the approximate count of the hyperlog log is now going to be like 1. If the same user within that hour window also has another event that fires, it's going to come in, but it's not going to get counted twice because the hyperlog log uses an approximation count distinct. And then another user comes along, and it's a different user, right? And when he or she gets put into the system, now we're going to increment the approximate count to 2. And of course, this is working on a much larger scale, as this is an oversimplification, really. So let's talk about like when we had these aggregations, how do we persist them? And we're actually computing these aggregations. If you remember from earlier slide, we're computing them every 2 seconds, which doesn't mean the aggregation's finished. We're just computing part of the aggregate every 2 seconds, and then we're merging the metrics in. So we're using FoundationDB for the online merging, and I'm going to kind of show you that here in a second, the best I can. Like I said, FoundationDB has this lexicographical ordering for time series scanning, and binary storage. We can store data in binary. So we use Java NIO for storing a small amount of bytes as possible. So let's talk about like how you would merge a metric. And this is the case where we're running multiple clusters. So when we have, like, for example, the Astronomical event, the Travis Scott event, we are able, the way we built the system is we're able to just stand up more clusters, independent clusters. And they, with the group-based consumption with Apache Kafka, they can essentially share the workload. So with this very small example, we have 2 clusters. They're sharing roughly 50% of the workload. But we can't guarantee what kind of event is going to which cluster. So we're actually computing just partial aggregates. So the partial aggregate on cluster 1 happens to be the sums 2 and the counts 3. And in cluster 2, the sums 3 and the count 7. And they're trying to update the row in FoundationDB and merge in the results from different clusters in order to have a complete aggregation. Again, this is happening every 2 seconds. So in the next 2 seconds, they're going to update the same row. In this case, the row is empty. And I'm showing that by showing the sum is 0 and the count is 0. So both of them are trying to write at the same time. Cluster 2 has actually has a conflict. It says, hey, that row's been updated since I tried to perform the write. I'm going to need to go reread that row and try this aggregation over, or this persistence over again. So it goes to write again. This time it succeeds. And now we have a complete result. The sum is 5 and the count is 10. So this is happening every 2 seconds. Typically, we don't have that many conflicts, and especially if you can kind of work the system to game it a little bit so you don't have so many conflicts. But the main thing as well is that we have the confidence that the ending result is completely correct. So that's very important. So when we're trying to scan these metrics, what does that look like? So this very simple table where we have essentially kind of like we have 6 rows, but we have each row, there's 2 sets of rows really. So in the first 3 rows, we have a one timestamp, and then the next 3 rows, we have a different timestamp. And you can see they're kind of ordered in a way where the first timestamp is coming down, and we're ordering by PS4, Switch, and then Xbox. Then the next timestamp comes down, and then we're PS4, Switch, and Xbox. So because the data is already ordered for us in FoundationDB, we can scan very quickly. If we want to do a whole range, we can do that as well. Or if we want to do a subset, again, we can do that. And as far as viewing metrics, we are able to do that as well using Grafana. So we found Grafana obviously is a very natural fit for time series use cases. Has a pretty straightforward plugin system as well. That makes it possible for us to create a custom plugin where users, instead of interacting with some UI that we make for viewing metrics, they can just use Grafana, and it looks just like maybe an Influx plugin or something like that. They just epic metrics, they type in the metric name they created, and then it, boom, shows up in Grafana for viewing. And the nice part too is they can create, using our UI, they can type in the Jpaths and all that stuff and define their aggregation. And by the time they move back to Grafana, their metrics are already going to show up. And the aggregation may, depending on what the window is, you may already see it immediately. And yeah, the nice part is it abstracts the API. So we're trying to get the user far removed from anything we've created as far as the API goes. We don't want them scanning FoundationDB and deserializing hyperlog logs and then getting the accounts. We have an API for that, and we use that. We just use Grafana. And Grafana also provides this very powerful thing, which is it's the ability to alert on thresholds. So game developers on Fortnite and stuff, they can create these metrics and define thresholds that tell them like, ooh, something's not quite right here. And maybe they need to page someone at 2 o'clock in the morning or something to tell them, hey, look, something's not looking right on the West Coast, for example, or something like that. And really what this means, once we built it, this self-service, completely self-service system, very low barrier of entry, it's really just metrics for everybody, as frightening as that may seem. But yeah, we have Fortnite engineers that use it. We have game services engineers that can use it. Unreal Engine, marketing team can even use it for some things. And really it's just like anybody in the company. That's kind of what we wanted to build. We wanted it so that anyone in the company could feel empowered to create a metric that could drive decisions later on in the game development process, as well as use it for alerting and keeping things stable and making sure there's no degradation. So of course, we've learned a few lessons along the way, to put it lightly. We learned first thing was to lower the barrier of entry, because that old saying, if you build it, they will come. It did prove to be correct for us, which was really nice. Lowering the barrier of entry really did work, and drives adoption. Another thing we learned was stateless Flink is just fine. And I'm not saying that's for everybody. A lot of applications need a state inside of Flink. But for us, we didn't really need it. We were able to update state outside of Flink using FoundationDB with very little effort. And we don't have to manage Flink state or anything like that, which is kind of nice for when we want to elastically scale up and down these clusters. Like I said, with the Travis Scott concert, we needed to increase the number of clusters that were online to handle that mass influx of people who come in for the concert that's only maybe 20, 30 minutes to an hour. And then after, we can scale back down. So we don't have to worry about state, which was really nice. Another thing we learned, even though it's really hard to do, like to bring yourself to do it, when you have this beautiful system you made, like you got to simulate failures. Like go break it in a way that you wouldn't expect it to break. Maybe simulate a NIC failure, simulate a hard drive failure, simulate just a low throughput NIC with latency and drop packets. You're going to cause things to fail in spectacular ways, because I guarantee you they will fail exactly like that at like 4 o'clock in the morning. You're not going to know what's going on. It really does help to simulate failures, because what ends up happening is you sometimes find out you might just need to tune your Flink app, and you can kind of get away from this the cluster in a degraded state, but not actually failed. And I think that was one of the most important things we did. We aggressively tuned the Flink application so that if any degradation even kind of occurs, just fail the application, and then the workload will shift over to another cluster in a different availability zone across a different region or something like that. Again, I want to thank Verica and Holger for the announcement. I was really surprised to be invited to Keynote this year. It's truly humbling, and I really, really appreciate it. So that is all.